Hey everyone, now it's going to be time for us to really start taking a critical look at what type of addressing it is we're working with. We're talking about those logical addresses and how things are going to be implemented and interconnected. But what we need to do is we need to develop a firm understanding of the IP addressing and subnet concepts in order to make certain that we know how to implement these infrastructures. Now, first and foremost, we have to understand one thing, and that is that, remember, switches do not break up broadcast domains. They break up collision domains. We need a router to break up a broadcast domain. Now, what's the significance of that? Well, remember, I mentioned earlier on that the more devices that we have on the segment, the more we are relying on our switches to make certain that either our collisions are absorbed or prevented, but there are other things that we have to take into account, like that flooding concept. Remember, broadcast messages are flooded. Multicast messages are flooded at layer 2 via our frames. Unknown unicasts are flooded at layer 2 via our frames. So what ends up happening is even though that we have our network broke up into multiple collision domains, i.e. a collision domain per port on the switch, what we have to also understand is the fact that our broadcast domains can become problematic for us. Broadcast domains are going to resort to, like I said, that concept of flooding. And when we send information back and forth, bear in mind all devices that are connected to our switches are going to be in a single broadcast domain. Now that means broadcast domains operate with frames, and frames rely on MAC addresses for packet delivery. Actually, I really wish that they didn't have packet, let's just say frame delivery, because it is layer 2. So the larger the number of devices we have, the more broadcast traffic we're going to have. And the more broadcast traffic we have, the more resources are going to be consumed and eaten up by the processes. And what ends up happening here is it really boils down to that we're all sharing the same domain. Now what we want to do is we want to take these larger infrastructure and we want to break it up into smaller subunits. Now in order to be able to do that, that's going to involve a device that we've been talking about known as a router. Now what ends up happening here is I'm going to be breaking up my network such that I'm going to have individual standalone networks on either side of my switch. In this instance, I have my engineering, I have my finance, and behind me I have my manufacturing portion of the network. But keep in mind, they're all going to be in their own networks. They're all going to be their own broadcast domains because routers filter broadcast domains. They break up large networks into multiple broadcast domains. Now what ends up happening is I have the same number of devices I had before, but they're not all contending for the same broadcast fabric. And they're also relying on IPv4 to move things across networks through the use of this idea of our router that we have. Now this means we have to create subnetworks. So in other words, we may be given a network of, say, 192.168.0.0/24, and what we're going to do is we're going to look at this and say, well, we can't mess with this because 24 tells me the first 24 bits, which is going to be the 3 octets, 8 plus 8 plus 8 adds up to 24, we can't mess with. But what we're going to do here is instead of having just one network, I'm going to be able to break this up into sub-networks. And that's all that we're doing. We're breaking up our bigger network into smaller groups. By having those smaller groups, now what we can do is minimize the overall impact of our layer 2 topology and any broadcast that may be taking place or driven in our infrastructure. Now, when we do this, we have to recognize the fact that in our topology or in our network, we have different numeric values. We already talked about the Class A, the Class B, and the Class C networks. And I mentioned the fact that the masks were going to be /8, /16, and /24 for each of those in turn. But when we look at this, that can be our main point of interest. Now remember, I noted, or I told us, that one portion of our network address, or our IP address, was our network. The remaining portion was best described or illustrated as our host portion. Now in the confines of the host portion, I could use all of these for my hosts, or what I could do is I could start striking off values and use a portion of these for creating my own networks. So that's what I'm doing. This whole notion of subnetting is where I'm going to repurpose bits by saying I want to reduce or support fewer numbers of hosts, but by virtue of stealing these bits, I can now support this idea of subnets. So it's really and truly no different. I mean, I have 4 sons. And if I go out to the grocery store and I buy a bag of jelly beans, I learned a long time ago that if I buy one thing, I have to buy 4 things. And if they're not absolutely identical, same color, same size, same flavor, same whatever, I'm in the middle of listening to the arguments and complaints from heck. So I don't want to be able to do that. And what I'll do is I'll go out and buy things like jelly beans and stuff like that. Well, the issue here is with 4 sons, if I buy a bag of 256 jelly beans, what I want to do is I want to subdivide that bag into 4 smaller containers. Well, if I do that, 4 divided by 256, or 256 divided by 4, equals 64 jelly beans. So I can actually take 4 mason jars and put 64 jelly beans in each one of them, and I don't have to listen to the grousing and complaining. Didn't rely on the store to break it up or to issue me 4 bags of 64. I just went out and bought a bulk bag of 256 and created my own. And that's all subnetworking is, and we do it by robbing bits from the host field. And that's all there is to it. There's going to be a few things that we need to understand, but it'll all come together for us very quickly when we look at it from a 30,000 foot view. So the first thing that I want to understand here is what values exist when it comes to creating a subnet mask. Now, my father and I, we restored vehicles for a long, long time while I was in high school, all the way up until I left for college and then ultimately joined the Army. Now, we did maintenance, we did the automotive, the engine portion, the brakes, everything. But when it came to the body work was where we were going to take this vehicle and we needed to spray paint on it. Well, obviously, we don't want paint to go everywhere. You don't want it to go on the tires, you don't want it to go on the wheels and the rims, and you don't want it to go on the windows or the rubber that seals the windows. So what we ended up having to do was mask it off, which involved taking tape and paper and masking off the portions where we don't want the paint to go and stick, and then we would spray paint the entire vehicle, wait for it to dry, take a razor blade, go around the edge, and then peel the tape off, and it would reveal a pristine window or a pristine tire. Masking is no different. A network mask means I'm going to be assigned a numeric value. So notice right here it says 255.255.255.0. Now what that's saying is that's decimal. So when I look at this, what I actually have is 1, 2, 3, 4, 5, 6, 7, 8 ones for the first field. 1, 2, 3, 4, 5, 6, 7, 8 ones for the second field. For the third field, the same. 1, 2, 3, 4, 5, 6, 7, 8. And then lastly, all zeros. I have such a habit of wanting to do decimals in these fields. So 1, 2, 3, 4, 5, 6, 7, 8. Now, why was I talking about masking? Well, when we took the tape and we covered up the windows, that's the equivalent of assigning ones. So if I have a value where I have a corresponding numeric value, let's say I have 1, 0, 0, 0, 0, 0, 0, 1, and then 1, 0, 0, 0, 0, 0, 0, 1, and then 1, 1, 1, 1, 1, 1, 1, 1, and then some value of, say, anything. What this means is the mask means where I have a 1, the corresponding value above it must stay the same. So in other words, it's quite like taking that masking tape and running it across the fields, and now what ends up happening is it says these are not allowed to change. So, and that's what the mask does for us. So a binary 1 reflects the network and the subnetwork part of an IP mask. Now, what would happen is that, notice this is a /24. So if I wanted to create smaller networks, what I would do is I'd have to be able to steal 1 or 2 host bits and repurpose them for the idea of creating more networks. So this range here, if I took 3, would change from /24 to /25, 26, 27. If I wanted to steal that many, to create that many networks. So that means I'd have 3, 2 times itself 3 times. So it's going to be 2 times 2 is 4, times 2 is 8. That means I could have up to 8 networks. So I'd be taking my /24 and breaking it up into 8 smaller networks. The same idea was as if I take those 256 jelly beans and put them into 4 mason jars. 64 jelly beans per mason jar. If I want to break it up even smaller, obviously I'm going to have fewer jelly beans in the jar, but I'm going to have more jars. A jar corresponds to a network, a jelly bean corresponds to a host. Now obviously I'm going to eat some of those jelly beans, so there's going to be a price of doing business, and we'll also talk about how that applies to networking also. Looking at how this is all implemented, we step in and realize that these values correspond to specific meanings. So again, when we look at the values of the masks, that means that these ones that we're going to be setting up here are going to be the exact same values. And notice this number line right here. Notice it's 1, 256, 258, 128, 192, 224, 240. I didn't mean to do that. Grab a pen so I don't accidentally do it again. Remember I did the number line? The number line was 128, 64, 32, 16, 8, 4, 2, and 1. And then below it I did 128, 192, 224, 240, 248, 252, 254, and 255. Well, if you do the number line like this, what that does is that gives you your octet values also. This is going to be the counting line. This is going to be your subnet mask line. So in this value, if I take these two values, these 2 bits, and I repurpose them for subnets, because remember, these are all host bits. This entire range right now is host bits. So if I repurpose that means that that's going to be my mask. So when I look at this and I go through and I said, well, originally we had a /24. So that would have been 255.255.255.0 as my mask. Well, what I've done is I've stolen some bits now. So what I'm going to do is I'm going to adjust this 4th octet. That's what I'm going to call my interesting octet. And what it's going to do, since I stole 2 bits, my mask is now going to be 255, 255, 255, 192. So that's what this number line does. I took 2 bits, so it's going to change my mask. If I took 3, it's going to change my mask to 222, 224. So that's going to be why this number line is so important for us. Now, other way I could also remedy this is that, remember, I've got 24 and I took 2, so that means I'm going to take 24, 25, and 26. This is referred to as CIDR notation or / notation. Most of our devices don't support it. In Nexus, you can actually use it in XOS, but in iOS and the ISR devices that we're going to be using, as well as the Catalyst devices that we have for the purposes of our demonstrations and for the simulations, you're rarely ever going to be able to use the / notation. You will find that we can use it when we start talking about DHCP services, but again, it's few and far between are the opportunities where we can actually use those. Now, when we start looking at this, we need to start looking at it in the context of our classes. So let's look at a Class A address. So when we go through and we look at a Class A address, first of all, how do I know it's a Class A address? Well, I know it's a Class A address by looking at the first octet, and I realize that it falls between 0 and 127. Remember, we did that math. So it's going to be the first bit in the field is always going to be 0. So 1, 2, 3, 4, 5, 6, 7, 8. That means all zeros would mean 0. If all of these values added up to 1, that means my ultimate range would be 127. Keeping in mind 127 is an issuable because it's a loopback. Now when we look at this, this gives me a decimal notation of this. This is my network. And we know that this network, because it's a Class A, I said has a /8. Now what that corresponds to is that if I take my class mask, which is this /8, and I apply these ones, what that is saying is that I cannot mess with any of these digits. They have to remain the same. So my default mask would be 255.0.0.0 or /8 in notation. Now that means, conversely, that all of these bits exist for the purposes of having hosts, which means I can have up to 16 million hosts. 256 times 256 times 256. Now looking at this, I may want to repurpose some of these bits. So later on I could come in and say, well, I want to take this range and I want to support up to this many 2 times 2 times 2 times 2 times 2 times 2, so 256 networks. That's subnetting. And that's how we would do it in a Class A configuration. Now, what about Class B? Well, first of all, how do I know this is Class B? Well, we know it's a Class B because we know that of the values that we have, the first two values have to be 1 and 0, which means these fields can be anything that we want them to. So 1, 2, 3, 4, 5, 6, 7, 8. So looking at this, that means it's going to be 128 plus a total possibility of 63. And what that's going to do is it's going to give us 191 as our max. So it's going to be 128 to 191 as our actual range. The first octet falls in that range, so we know obviously that this is a Class B. Class B has a default mask of 255.0.0 or a /16 because the first 8 bits are all ones. That's how we get to the 16. So that's what's illustrated right here. Now we also see the CIDR notation, the classless interdomain routing notation. So again, what we're doing is we're masking. So it's the equivalent of taking the masking tape and saying, well, because these bits are all ones, that means we cannot mess with any of these values. Now obviously that means I can use anything else because they're all zeros under them for my hosts. So these are hosts. However, I could arbitrarily say, well, I want to use 2 of these to create a subnet or a group of subnets. I could take 2 times 2, so that lets me create 4 subnets. And then what ends up happening is the rest of these become hosts. So all I'm going to do is I'm going to arbitrarily come in here and I'm going to say these 2 values have to be 1 and then the rest can be all zeros. So that's going to change my mask in this situation from /16 to 17, 18. So it'd be a /18. So as you can see, I am now sacrificing 2 or 4 networks, or I'm actually sacrificing the ability to be able to have more hosts by creating more networks. So I'm robbing Peter to pay Paul. That's all I'm doing. And I'm illustrating this point before we actually go through so that you guys can at least visualize it in the context of what the default masks are, because we've got one other class that we need to look at. The other class that I want to look at is going to be the Class C range. Now the Class C range, again, what Cisco or what the industry standards body has done, they've taken the first octets and they say, well, the first 3 have to be 110. That means the rest can be whatever we want them to be. Ones or zeros. 1, 2, 3, 4, 5, 6, 7, 8. So these are going to be the rest of the values. So adding this up, that means 192, which is going to be 128 plus 64 plus 31. That's what this is going to add up here. Means my range is going to be no less than 192 and no more than 220, 33, yeah, 223. 192 falls into this range, so I know this is a Class C address. Class C addresses have a /24 or a 255.255.255.0 mask, as we can see here and here. So in other words, like I said before, what we're doing is we're coming up and saying, well, when we cannot mess with any of these digits have to be the same. So that can never change. However, same as always, these digits are going to be available to me for hosts, and I can also repurpose them by stealing 1 or 2 of them, or 3 or 4 of them, and using it to create subnets. So in this instance, I'll steal 4. So if I steal 4, it's going to expand my mask. My mask is going to go from /24 to 25, 26, 27, 28. And now what I'm going to do is I need to understand what's happening here with regard to how I do the math. So all I'm going to do is I'm going to take 128, add 64, because that's the 128 place, the 64 place, the 32 place, and the 16 place. So that's going to give me my range. And what I'm going to see is I'm going to see 124, 192, 224, 240. And you guys are going to have to become this good with the math. So that means that the mask for the subnet would be 255, 255, 255, 240, or /28. So again, This is all relatively straightforward. You just need quite a bit of practice to be able to work with it. The other element that's going to be infinitely important to us is going to be the idea of a default gateway. Every PC has to have a default gateway or it's not going to work. A router needs to have some kind of default gateway at the minimum in order to work. So when we start looking at this, really and truly, let's step in and figure out exactly what it is we're talking about. Notice that PCA, that's the machine that I'm on. Here's my address, here's my IP, here's my mask. So my IP, my mask. And it says I have some data that I want to send to the machine that has 10.1.1.2. Now when I look at this, what's going to happen is the computer is going to look at its internal routing table. Every computer has one. And it's going to make a determination. And this is it's going to say the destination host is in my local network. Because if we look at this, 10.1.1.2, so if I say 10.1.1, so let's just do the math, 10.1.1.1 and 10.1.1.2, and I have a /24 mask. That means I can't, if I take a look at the first 4 or the first 3 octets, I can't touch these. So they're in the same network. All of these numbers match, 10.1.1.1, so I know that they're in the same network, which means I can send the information directly through. So I can send this data directly using the correct MAC address, and I'm going to do that at layer 2. Because this network and this network are all part of this IP address, this host is all part of the same network. Now, let's look at the converse of this. What happens if that destination is not on the same network? So let's observe. Here I said I have some data to send to 192.168.3.2. Well, my address is going to be a 10. This is my mask. And I'm going to look at the network and say, well, I'm a 10.1.1.0. So it's going to be 10.1.1.0/24. That's my actual network. So the system's going to say, well, it's not a local network. So I can't reach it directly. I need to go through a device that's going to be able to do that. And that device is going to be my default gateway. In our cases, it's always going to be a router. The default gateway is going to be the device that says, okay, I know how to get to the outside world. So what's going to happen is this particular component, this particular message is going to be sent to the default gateway. The default gateway is going to check its table, and then it's going to decide whether or not it can send that information on. In this case, we're operating under the assumption that it can. Now, the thing that we need to understand here is let's say that I wanted to send information to it, but the information has to get back. Well, this information is going to go through, and it's going to arrive, and it's going to look at the destination, and it's going to be the router that says, oh, this is destined for a device that is physically on my network, and then it's going to send it to here, which is going to actually send it again using layer 2. So in other words, the switch is going to be part of the communication, and we can't lose sight of that. And it's going to be the default gateway that's going to help us out here. Now, what I want to do right now is I want to explore how we do this subnetting, because it's really not that hard. All we have to do is just understand the possibilities. So what's going on when I work with a Class B address? Now remember, a Class B address is a 255.255.0.0, or more commonly annotated in shorthand as /16. So again, this is going to be for a Class B network. Now when we look at this, what we see here is like I said, it's going to be 255.255.0.0 by default. That's the default mask, which means this is going to be 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. I've got one too many in there. 1, 2, 3, 4, 5, 6, 7, 8. We got 8 here. So this mask means this number can't change, this number can't change. Now, the numbers that can change are going to be the numbers that are going to have corresponding zeros under them in accordance with the mask, which means anything else past the first 16 bits. Now, what I'm going to do is I'm going to play around with the fact that I'm going to borrow bits. So I've got a /16. What happens if I borrow 1 bit? So if I borrow this bit, make this a 1, and now this bit is going to be green. So now this bit is part of my network. Well, I can have 2 networks. Now that means that leaves me 15 bits for hosts, which means I can have up to 32,766 hosts minus 2 hosts. Minus 2. Now the rationale here is remember, we have to have a network that's going to be the all zeros, and we also have to have the broadcast, which is going to be the all ones. That's the 2 we can't use because these can't be physically assigned to any devices. Now also, what happens if I borrow 2? So I picked up we'll borrow another bit here. And let's say I'm going to borrow the 2. Well, that means now I have 2 times 2. So that's what this adds up to right here. So all I'm doing is, this is the possibility of 2. So 2 times 2, which means now I can create 4 networks. That leaves me 14 bits for my hosts. 14 bits means I can support up to 16,382 after removing the 2 that I lose, one for the all zeros, one for the all ones. That's going to be my network and my broadcast. So as you can see, I can create or borrow in this scenario and ultimately support up to like 65,636 networks. But the problem is that if I did that, I don't have any way to have hosts. So that's not even going to work. So I can't take all of my bits to have it work. If I have 15 bits, I take all 15 out to here, and I use them. That means I can have 32,768 networks, but I only have 1 possible value that I can use, and I still have no hosts, so I can't take 15. However, what happens if I took 14? Well, by taking 14 bits, I can have 16,384 possible subnets, and I can have the idea of having up to 2 hosts per each one. So as you can see, using the different ranges, A's versus B's versus C's, if we progress this logic from class B, what we see is that we can have the capability of the more hosts we have, obviously the more networks that we can actually create. But keep in mind, the more networks we create, the less users we can support per network. Again, no different than taking that 256 jelly beans and putting it into 4 containers. Now, in this instance, in a class B, I would actually be using something like 35,000, what's the number here? It'd be 65,536 mason jars. And each one of those mason jars would contain X number of jelly beans. So, I mean, after a point, it kind of becomes ridiculous. But we will learn that there's going to be situations where we do want to have the idea of just having 2 links. And it all really boils down to when we start actually making this work, when we apply subnet masks. Now, what does a subnet mask do for us? Well, it determines the IP address space. Now, it's going to be something that we set up, and it's pretty much arbitrary. It's arbitrary based on the number of networks that we need and the number of hosts that we need in each network. It's also going to allow us to be able to mitigate wasted addresses. Specifically, we'll look at that in the context of variable length subnet masks, VLSM. Now, when we look at this, everything is based on class because we're going to start with the idea of our default mask. The default mask controls pretty much everything. So if I'm going to borrow bits, I'm going to do all of my computation based on the default mask. So if I have 16, or if I have 24 for a class B and a class C and I start stealing bits, remember it's going to go up, but it's going to go up by adding the number of borrowed bits to the base mask. So if I borrowed 2, this would go up to 18. If I borrowed 2 in this situation, this would go up to 26. And the way we do that is to determine the binary and decimal value of the subnet mask. We can apply that mask to the IP address to determine what part of it is going to be the network and subnet and what parts are going to be the host. That's exactly what we just did when we did our walkthrough. The other part here is we assign addresses to specific interfaces for all devices in our infrastructure. Keeping in mind that if you're on a shared LAN, everybody needs to be in the same network. So keep in mind, we are going to lose 2 of our values for our host count simply because we lose the all zeros for the network and the all ones for the directed broadcast. The other part of the equation is that if we have 31 possible issuable addresses and we have 32 computers, we're going to have to go back and adjust our math so that we can break it up to where we can support the optimum amount of users. Cisco's going to be famous for asking us to do computations that are going to say in the future, we currently have this many, but in the future we may add this many users. Make sure that we don't have to redo the subnet mask range. And that's going to be something that we're going to definitely want to make certain that we entertain before we go into take the CCNA exam. Excuse me. So when we start looking at how this is going to be configured, the first thing that we have to recognize is that we can be issued an address. Now the address that we're issued in this instance is going to be the IP address with the following mask. 172.16.36. So 172.16.36.24/24. So in other words, what's happening here is that the IP address with the subnet mask, this is what we have. Now 24 means this is all ones here. So 255, all ones here, 255, all ones here, 255. And then we have 0. So that means these cannot be touched, and this defines the network. So in other words, this is going to be a class B address, but I have a /24 subnet mask. Because it has a /24 mask does not make it a class C address. This value right here is what determines what class it is, whether it's been subnetted out. But the whole point here is that keep in mind, when we look at this, our default mask was this. So since our mask is bigger than 16, we know that we are stealing all of the third octet to create subnets. So when we go through here, the following tables show the 8 steps that are used to determine the subnet addresses of the given IP addresses in this example, keeping in mind 172.16.36.42 with this mask. So let's walk through the math on this and see what we see. So how do we do this? First of all, we write down the octet that is being split and all remaining octets in the binary that we're going to work with. So what we have here is that we have the 3rd and 4th octet. So when we look at that, that's going to be the range that we have to play with. So we're going to write down the mask or the prefix length in binary. So notice we went all ones for the first 3 octets and zeros for the 4th, which means these values become the network. So everything where we have a 1 under it becomes the network. What we're going to do is we're going to draw a line to delineate the subnet from the host bits. So when we look at this, in this range, 36, because remember it was 172, what was the actual, bear with me just one moment. Should have been 172.16. So here, it's 172.16.36.42. Now what they're doing is they're saying because all of these are 255, that means these numbers have to stay the same, but these are the numbers that we're looking at. That's what this means, the 36.42. So when we look at this and we draw that out and we write it all out and we look at the mask, what we see is this 36 can't change. So the bits that we're going to be manipulating are going to be in the 4th octet, and that's what this is trying to illustrate. So the split octet in binary is, this is 36, this is 42. This line divides the two because of the mask. So this is subnet mask. And that takes us out to 24. We started with 16, we add another 8 to it, now our subnet mask is 24. Now once we've got that done, then what we want to do is we want to take a critical look at how we're going to represent this mathematically. So how do we do the determination? Well, the first thing is we copy the bits 4 times. So when we look at this, what we see here is that we're going to have the following configuration. We copy the bits 4 times. In the first line, define the network. So the network obviously has to be the all zeros. So remember, the network is all zeros. The broadcast is all ones. So mathematically, when we start looking at this, what we're going to see is that the address is going to be this idea of, since the break is right here, it's going to be 172.16.36.0. The first issuable address is going to be .1, so it's going to be one more than the network. The last issuable is going to be one less than the broadcast address, which is going to take us down to binary 1.1.1.1.1.0. So that means when we go through and we start looking at this, we're going to increment the subnet bits by 1. So in other words, what we're going to find here is since we took all of these bits, we're going to have network 172.16.0.0. We're going to have 172.16.1.0, 172.16.2.0, all the way out to 255.0, but ultimately we would not be able to have that range. So looking at that, that's going to be the actual number. So let's look at what we've got here. What's the next part of this? The next part of this is when we start looking at how we're going to issue it. So this is the actual range. So when we look at the deployment, we've done all the binary. Let's look at what's involved in the actual configuration. Like I said, our network would be 36. The first issuable would be 36.1. The last one is going to be one less than the broadcast. So that's going to be 254, broadcast being 255. The next network would be one more than this range here, which means it would be 37. Now, I don't necessarily care for this kind of illustration because it's pretty complex. But when we look at it, 172.16 dot, let's see here, what did we have? We had 36.42. Now, we had a /24. So that means I have this bits, and these bits that I can't mess with. But I'm stealing all 8 of these to create my own networks. So because I know that, because this is a Class B address, which ordinarily would be only a default mask of 16, which means I've taken 8 for the purposes of creating my own networks. That means that I'm going to have 2 times 2 times 2 times 2, 1, 2, 3, 4, 5, 6, 7, 8. So that means I'm going to have up to 256 total networks that I could play with. Now, in order to be able to get 256 total networks, what I'm going to do is I'm going to use the math, because remember, my value here is 255, because it's 0 to 255, not 1 to 256. So if I take 256, which is my possible, and I subtract 255 from that, that's going to give me a block size of 1. So that means this value right here, the third octet, because that's where I stole the bits from, is going to increment in values of 1. So that means I'm going to have 172.16.1.2.3.4, all the way down to .36, which I know is my network here. Now my other network is going to be, we have to recognize that since this is all zeros, 1, 2, 3, 4, 5, 6, 7, 8. We also have the all ones. So if I have 36.11114, there's 8. That means I have a maximum range here that's going to be 255. My next network is going to be 37. The next network after that's going to be 38. So as you can see, the math becomes pretty easy when you just look at it from the point of view of the block size. So when we go through here, like I said, this adds up to 255 binary, because again, when we look at it, look at that number line. So I had 128, 64, 32, 16, 8, 4, 2, and 1. And if I add all of these up, it's ultimately going to issue, because these are going to equal 127 plus 128. So the moment I come through here, it's going to be 8 plus 7, which is going to be 15. Then we have 4, 5, and 2. Adds up to 255. So all I do is I take the block, I take this and subtract it from 256, and it gives me my block size. In this instance, my block size is 1. And that's going to be the area or the interesting octet value that it's going to actually increment. All right, let's take a look at the rest of this. Should do another scenario. That's what we're going to do. So let's take a Class C address and see what happens when we actually break it up. So in the confines of a Class C address, we know that we have a native mask of 24. I see I have a native mask of 29 now, which tells me I'm stealing 5 bits. So when I look at this, what I'm doing is ordinarily I would have the value 192.168.221.36, and it's a /29. So that means this is going to be all one, so it's 255, 255, 255, and then when I come through here, what I'm going to do is, since I have 29, I know I'm taking 5 bits. So of the values that I have, 1, 2, 3, 4, 5, 6, 7, 8, I'm taking 5 of them for the purposes of creating subnets. So that means I have this value right here, which is going to be 2 times 2, which is 4. But if I go through and use the number line, remember it was 128, 192, 224, 240, 248, 252, 254, 255. So I stole 5 bits. So 1, 2, 3, 4, 5. That gives me 248. So my mask now is 255, 255, 255.248. Now this is interesting because I can actually take this value, let's say take 256, subtract 248 from it. What am I going to find? I'm going to find an 8. That's my block size. So in other words, this value right here is going to be where I'm going to do my incrementation. It's going to be on basis of 8. So what I would do is I would have 192.168.221.0, 221.8, 221.16, 221.24, right? 8 plus 8, 16, 16, 24, and then we would have 8, which would be 32. So 22 or 221.32. Okay, the next value here would be 227, add 8 to it, 8, 9, 10, which would be 40. Now when I look at this, 37 falls in this range right here. So I now know that my network would be 192.168.221.32. I know the next network would be 192.168.221.40. I know that my broadcast address is going to be 192.168.221.39. It's going to be one less than the next network. That's my broadcast address. I know my first issuable address is going to be 221.33, and I know that my last issuable is going to be 221.38. And again, really and truly, all this is going to be the fact that I'm going to have this many networks that I'm creating. So I'm incrementing by 8s. So we just resolved that without having to do anything other than the base math. I'm going to erase everything except for the math and make sure that we got the math right. And again, I'm trying to drive home the importance of that number line. That number line will make your life so much easier if you just pay attention to how you're using it. Again, it's not really a shortcut just as much as it is just a reference. So what I'll do is, let's see what happens. See if my math is correct. All right, again, I'll create a new page and then come back. So write down the octets, do all of that, do all the binary mathematics, and then we should see our resolution coming up right now. Should give us the answer on this particular slide. And let's see and compare it to my values. So what I see is 32 is my network. 33 is my first issuable address. 38 is my last issuable address. My broadcast is 39. The next network is 40. Lickety split, and you're done. So again, this is definitely something that we want to play with. But we've got more scenarios. Let's see what's going on next. All right. So when it comes to working with it, let's see if they have us do anything else, because it gets a little bit more complicated when we start working with Class A addresses. But what we want to do now is let's look at this, the entire scheme that we have. So when we blow through this, the IP address with the subnet mask, they're giving us what the IP address is right now. Well, first of all, I know it falls between 191 and 223, so I know it's Class C. That tells me that since it's Class C, it should have a native mask of 24. Notice I have a native mask of 20. I have an adjusted mask of 27, which tells me I'm subnetting. So if I draw my number line back out, remember it was 128, 192, 224, 240, 248, 252, 254, and 255. So what I'm doing is I'm taking 24, so I'm stealing 3 bits. So if I look at it here, that tells me that my network mask is /224. So now my mask would be, instead of 255.255.255.0, it's now going to be 255, 255, 255, 224. Now I can take 256, subtract 224 from it. That's going to give me 2. This is going to give me 3. Cancel out. So my block size is 32. Now, my mask is in the 4th octet, so that tells me that's where I'm going to do my manipulations. So looking at this right now, we've got a pretty big number here. So I would have to go through and do this mathematically, or I could use my calculator. Now, if I wanted to do this mathematically, all I would do, because we're counting by 32. So we're counting 0, 32, 64, 96, 128, so 128, and then we add 32 to that, so it's 8, 9, 10, 3, what was that? I hate math. 128 plus 32, so it's going to be 8, 9, 10, and 60, so it's 160, is that right? I don't want to use bad math, so just give me 1 second here and I'll verify. Now you won't have access to the calculator in your test. However, you can do it out longhand. So basically 128 plus 32, 160. Yep. All right. Now the thing is this is the number that's important, 136. So 136 falls between 124 and 150. I mean, sorry, 128 and 150. So I know this is my network. So let's write what we know, and we'll go from there. And I'll show you just how easy it is once you've got the numbers. All right, so we'll leave that there. All I'll do is I'll come up here and I will say that I have a network of 192.168.5.128/27. Now I know my next network is 150. So that means my broadcast address is going to be 5.149, one less than the next network. My last issuable is going to be 5.148. My first issuable is going to be 5.129. So it's going to be one more than the network. So let's see what we've got here. So when we go through and we look at our configuration here, let's see what I've got. 36. 128. This is wrong. Should be 129. My last issuable, 50, 49, 48. Man, they hosed this up. My next dead address is going to be 160. Oh, I said 150, so I messed it up. My bad. 160, so 159, and then 158. Nope, I hosed it up. Let me double check my math one more time. Let me guess, I closed the calculator. I hate it when I make mistakes on film. Never good. So, I said 128 plus 32, 160. Yep, I was the one that messed up. So, what do we have here? Let me drag this off the screen. So this should have been 160. 8, yep, all right. So that meant 160, 159. So they got this wrong, which was what should have been 129, then 158, then 159. So short of a mathematical faux pas, you can see that it's not that complicated to do these calculations. Now, the problem becomes in situations like this. Because if I were to take our networks, and I were to break our networks up evenly, remember, let's say I have, in this scenario, one of the things that I did wrong in one of my presentations was I said I wanted to do 4 networks, but that was to support hosts on the other end. I didn't take into account the links that were across the routers, and that's things that we have to actually do when it comes to making all of this work in the real world. So as you can see, I have a network from here to here, from there to there, from there to there, and I also have the devices on the other side. So if I want to support things, I not only have to take into account the networks where the hosts are going to be, I also have to take into account the links that are going to the different devices. So when we look at this, the problem is this. If I did everything in a uniform fashion, so here's the situation. Let's take a look at this value. It's 172. So remember, my range goes from 0 to 127. For a Class A. A Class B is going to be 128 to 191. A Class C is going to be 192 to 223. So looking at this, 172 falls in this range, so I know I got a Class B, which means I should have a default mask of 16. However, I see I have an actual mask, a subnet mask of 24, which means I've borrowed 8 bits. Now I can make a crap ton of networks, but the problem here is that by virtue of the fact that I've done this, I'm not using my bandwidth efficiently. So what I have here is I have a network that has a 24, which means I can support up to 255, technically 254 by the time I subtract my 2, on this network, IP addresses. But this is a point-to-point network, so that's a waste of IP addresses. So one of the things I may want to do is I may want to set this up to where I do not have a uniform mask range. So notice here, everything is 24. That means that's going to be a fixed length subnet mask. Now, they don't really work that great in the real world, especially since we don't want to waste IP addresses on links that only have 2 IP ranges. Why would I use a /24? The other thing that we need to understand is all modern routing protocols communicate this idea of a variable length subnet mask, whereby I have the ability to go in and carve my network up in varying degrees or varying levels of scale. So in other words, I could have some /24s, and I could also have some /252s. I'm sorry, I could have 255, 255, 255.0, or I could have 255, 255, 252.0. Or I have 255, 255, 255, 252. It just depends on how I want to be able to break my network up and get a more efficient use and spread of my individual IP addresses. So what we want to do is let's entertain this. Let's entertain this as a math problem. So if I come up and I look at my situation right here, the ideal scenario would be for me to have variable subnet lengths. So notice here I've got 24, 16, 24, 30, 27, 27, 27. Now this means the subnet that I was given was 172.16.14.0/24. That's what I was given. But notice I've expanded these. So when I look at this deployment right here, notice I have /23, 27, I have /30. So what I've done is I've broken these up. Now the way I've done that is that one subnet has a subnet mask of 27. So that's these guys right here. The other has a subnet of 30. That's these here. So when I start looking at 30, let's look at seeing what it takes to get to a 30. So if I take 128, 192, and I take a look at, let's see here. Well, 30 would be easier. Let's just do it using the number line. 128, 64, 32, 16, 8, 4, 2, 1. So 24, 25, 26, 27, 28, 29, 30. So when we do this, these are the bits that we're stealing. So how many hosts can I actually have? I'm only going to be able to support with a 30, let's see, 24, 25, 26, 27, 28, 29, 30. That's here, so that's 4. So that's going to be 252. So it'd be a slash 250, well, not slash 252, it would be 255.255.255.252. Now what's happening here is if we start looking at that, that leaves me these guys right here. So 2 times 2 is going to be 4 minus 2 equals 2. So that's all the hosts that I can support. And guess what? That's all the hosts I need on these point-to-point links. So what we want to understand is exactly how we can go through and do these computations in an organized fashion to be able to support our network. So in this situation, what we're going to do is we need to take into account a number of things. First of all, we need to be able to support up to 50 hosts in each of our different locations. We need to have an address range that's going to allow us to effectively use our point-to-point links without having to burn up tons and tons of IP addresses. And we've been issued a network range that we're going to be using. So what I'm going to do is I'm going to write this down such that it's going to continue with us through this whole presentation. So 172.16.32.0/20. Now let's take a look at what we stole and what we've got first. This is our region, our entire region's subnet. So first of all, 172 is class B. I knew it had a native of 16. Now I've taken 20. So that's 16, 17, 18, 19, 20. So I'm stealing 4 bits. So on my number line, and I'll write it down here, on my number line, remember it was 128, 192, 224, 240, 248, 252, 254, 255. So I stole 4 bits. So it's going to be 1 bit, 2 bits, 3 bits, 4 bits. So my mask is now going to be 246. So when I look at this, what do I see? Well, I see the fact that my mask now is 255, 255, 240.0. That's what this /20 is representing. But this is the range that we need to work with. So now let's break it up and take a look at it mathematically and see what happens. So my first idea here is I need to borrow some bits. I've got the /20, but what I'm going to do is I'm going to steal some more. So what I'm going to do is I'm going to take my configuration, and what I'm going to do is I'm going to borrow some bits. So the bits that I'm going to borrow is going to be as follows. Notice here I have my subnetted address, and I'm going to subnet it down even further. So what I'm going to do is I'm going to create a series of /26s. So that means I have 8, 16, 24, 25, 26, 24, 25, and 26. Bear with me just one moment. So I'm stealing 4 bits. Trying to look at the math here. So we're stealing 4 bits for the subnet. So these are the 20s. 16, 17, 18, 19, 20. 21, 22, 23, 24, 25, 26. Okay, that's what we're doing. So what's happening here is this. This was the original subnet that we were given. So it was /20. So it's going to be, let me grab my white pen so it'll show up here. So it's going to be 8 plus 8 is 16 plus 4 is going to be 16, 17, 18, 19, 20. So that's going to be our 20. Well, I need to actually steal some more bits. And notice right here what I'm doing is I'm stealing 6 of them. So now I'm going to change my mask to 32/26. This jump from 20 to 26 was confusing me because I saw 16. So when I go through and I start looking at this, now what I'm going to do is I can actually create subnets. I'm going to create 5 subnets. So when I go through and I set this up, what I'm going to have here is I'm going to have 5 networks. Remember, these are all zeros that we're implementing. So I'm going to have 172.16.32.0, 172.16.32.64, 128, 192. And what we're going to see here is that when we look at how this is implemented, let's bring our number line back. All right, so I've stolen 6 more bits. So that means my mask is 255, 255, and it was 240.0. Now what I'm doing is I'm going from here, that's 20, I'm stealing 6 more bits. So I'm stealing 1, 2, 3, 4, 5, 6. So now my mask is 255, 255, 255, 192. Now if I go through and I take figure out my block size, 256 minus 192, that's going to leave me with 4. This is going to be 19. See, should be 64. Yeah, 64. So that's my block size. So I'm going to increment my network on the basis of 64. So I'm going to go from 0 to 64, from 64 to 128, from 128 to 192. Now the problem is that what I've did is I've crossed a boundary here. Why? Because I'm actually going between 2 octets. So now, rather than it being, when I add 64 to this, if I take 192 and add 64 to it, that's going to be 6. That's going to be 256, which I can't have, which means I'm going to have to increment my value here to 1. So it's going to go to 33. So that's the reason and how we got this particular range. And these are not hosts. These are just the host bits. This should be the host bits that are remaining. These are the actual networks. So if I want to look at issuing addresses here, I'm going to issue 32.1 as my first issuable. It's going to be 32.63 is going to be my broadcast. My last issuable is going to be 32.62. My network is going to be 32.0, so on and so on. Now this gives me the capability of being able to issue these addresses. Now it doesn't address the point-to-point connections, but let's get this issued and get it in. So right now what we see is that we've added these 5 networks, or 4 networks. So we have the 32.0, the 32.64, the 128, and the 192. Now what that's left is that's left 1 range of addresses that we haven't issued. So the entire subnet is here. The VLANs that we derived from it have all been implemented. So we've got 50 support here for 50 different devices, but notice we still don't have anything for these links. But remember, we made 5 of these. We have deployed 1, 2, 3, and 4. So what we can do is we can take that 5th one, so we can take the 5th network, and we can subnet it even further. That's the idea of variable link subnet masking. So in order to be able to do that, what we're going to do is have to do some more math. And remember, we need to support up to 2 hosts on each of those individual links. So here's what we're going to do. We're going to take that network that we had left over, the 172.16.33.0/26 network. And what I'm going to do is I'm going to steal some more addresses. Well, what addresses am I going to steal? Well, I'm going to steal, here's my subnet, I'm going to steal 2 more. So that's going to take me from 26, let's hold on here. So the subnetted was 26. So this was the original subnet. So that's going to be 8, 8, 16, 17, 18, 19, 20, 21, 22. We're going to 30. So we're kind of doing it backwards here. What we want is we want to have 2 hosts that we're going to support. In order to be able to get 2, we're going to have 2 times 2 as our minimum, because remember, we lose 2. 1 to the broadcast, 1 to the network. So that means we want to steal 2 additional bits. But if you notice here, that's not what we're stealing, that's what we're leaving. So let's look at that. So 128, nope. Bear with me just one moment. Eraser. So if we look at the math, we got 128, we have 192, we have 224, 240, 248, 252, 254, 256, 255, excuse me. All right, so that means we have this many bits left in our configuration. So those are the bits that we're setting aside for our variable length subnet computation. So that means we're taking everything else and we're adding it to our subnet. So what's happening is we're creating a /30. So if you look at this, what happens here is 1, 2, 3, 4, 5, 6, 7, 8. So that's all 8 of our bits. So we got 16, 17, 18, 19, 20, 21, 22. So that's what we're doing, is now we're at a /22. If we look at a /22, like I said, that means it's ultimately going to put us in the range of the, it's not /22, it's 30 and a third octet. So what we're doing is we're taking this network, the one that we had left, and we're just breaking it up into smaller pieces. And if we look at our block size, what it's going to be is it's going to be 256 minus 252, this value right here. So that means we have a block size of 4. So when we go through here, that means we're going to break this network up into subnetworks that are going to be in increments of 4. So it'll be 0 to 4, 4 to 8, 4 to, or 8 to 12, 12 to 16, 16 to 20, that type of stuff. And it's going to be in the range of /30s, and mathematically that's going to only give me 2 host IP addresses. So all I need to do is assign these networks to my 4 links. Notice we only calculated 4 links because we have 4 networks and we have 4 links connecting our routers together in our infrastructure. So all we're going to do is we're just going to apply those networks here, 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 and here. So we can support 50 hosts here using the /26. Here we can support 2 hosts using our /30. So all we did is we just created 5 /26 networks, and then we took that other /26 network and we just broke it down to where it would only support up to 2 hosts. Now, in that scenario, again, that's conserving addresses, and if we add any more point-to-point links, obviously we can bring all of those point-to-point links up by adding even more of these prefixes or even more of these networks. So just bear in mind that that's going to be the main idea of how we're going to support variable length subnets in our infrastructure. Now again, at first blush, the math may look kind of complicated, but remember, if we resort and we take everything down to its block size, everything becomes very, very easy for us to employ. Now, I'm going to do a little bit of video later on where I'm going to walk through, not the shortcuts, but using references in order to be able to facilitate the mathematics, because you're going to see just how quickly you can actually find these issues. But until then, I want to ask you guys to see me in the next video. Bye.